Hello everyone, welcome to the Sigmoid Tech Talk. My name is Ankit Mehra and I work as a data scientist with Sigmoid. In today's video, we'll talk about BERT with the focus on subword tokenization method. Now coming to our first slide, here it is the continuation of our previous video where we talked about vectorization methods with the focus on word-based tokenization methods. Here I would like to talk about few drawbacks of those methods. So the first one is the inability to handle out of vocabulary words. This essentially means that the model is able to recognize the words that it has seen during its training process, but the new words are treated as unknown and represented using a random vector, which can be suboptimal. The second problem is no shared representation at subword level. What this means is some words can be represented as a combination of other words. For example, care and less can be used to create careless, but this kind of functionality is not possible with this method because each word is represented as an independent vector and such operations are not feasible. Now let us move to our second slide. So here I would like to talk about the key elements of BERT that helps it to understand the text better. So the first thing is transformer. Transformer uses self-attention, which helps in relating different words in a sentence in order to compute its representation. So let us look at this example. Here the common word bank is used, but in two different contexts. So what self-attention does is it looks at each word and its neighboring word to draw the meaning and uh, use it in the context of the sentence. Now moving to the subword tokenization. Subword tokenization can be used to eradicate the problems that we have seen in the slide 1. Now looking at subword tokenization, what it is. So subword tokenization is essentially a solution between word-based and character-based tokenization while eradicating the drawbacks of both word-based and character-based tokenization method. In practice, the common words are tokenized as the whole words, but the rarer words are broken into small chunks and can be used to create the relevant dataset. BERT uses WordPiece tokenization method, which can be seen as the combination of subword tokenization methods, namely Byte Pair Encoding and Unigram. Now let us look at what is Byte Pair Encoding. So Byte Pair Encoding is originally a data compression technique which uses most common byte pairs to represent the data. So suppose we have a text document in which we have the words juck, buck, fun, run, and huge. So in the first step, all these words are listed along with their frequencies. In the second step, we break down these words at character level and note down the frequencies. In third step, we start merging the characters to create the byte pairs. So at each iteration, the most common byte pair is picked. So for example, we can see UG is the most common byte pair. It is present in jug, bug, and huge, and its frequency comes out to be 20. After selecting our most frequent byte pair, we readjust the frequencies of the characters that are used to create that byte pair. So here we subtract 20 from both U and G. This is repeated at each iteration, and the process can be controlled using two parameters named as defined token limit and number of iterations. So suppose if we set defined token limit as 2, then in that case we will not reach this final table because it here we encounter a byte pair of length 3. Also, we can use set number of iterations. So suppose if we set it equal to 2, then the process will only occur 2 times and we will end up with this table as our final table. So suppose this is our final table, that is it runs for n number of iterations. So we can see from here that these tokens can be used to create our original words, and also it can be used to create some new words like RUG can also be created. So essentially with bigger and diverse data set, we can create tokens that are capable of handling the drawbacks that we have listed above. In our next video, we'll look at the drawbacks of byte pair encoding and how Unigram solves this problem. Here, I would like to start with the drawback of this algorithm. So, as we saw in our last video, byte pair encoding picks the most frequent byte pair in each iteration, making it a greedy algorithm. So, the greedy approach can result in an ambiguous final token vocabulary. So what I mean by that is, let's suppose we have an input word huge. So after implementing BPE, suppose this table shows the final vocabulary. So if we try to recreate huge, there are two possible ways. One is H, UG and E, and the second one is H and UGE. In the case where there can be multiple representation for the same word, there is no way to prioritize which representation to be used. This can result in multiple embeddings, different embeddings for the same word, which can impact the model's learning process. So now we'll talk about Unigram and see how it can address this problem. So Unigram is a fully probabilistic model. It uses probabilities instead of frequencies. It tries to optimize the overall likelihood value to reach the final vocabulary set. So suppose we have a text document in which we have the words jug, buck, fun, run, and huge. So in the first step, we note down all these words and their respective frequencies. In the second step, we start breaking these words into all the possible combination. For example, for jug, we can break it like J, U, G, J, U, and U, G. And for bug, we have B and BU. And we have UG and UG common in both jug and bug. So those are already being captured. So this way we break down the words into fragments and note down their frequencies. In the third step, we calculate the probabilities of all the combination for each word. So for example, let us look at fun. So fun can be represented in three different ways. That is FUN, FU and N, and F and UN. So let's focus on the representation F, U and N. So to calculate this probability, we basically multiply the probability of individual character. So for probability of F, we can see it as a frequency of F, which is 12 divided by 190, which is the frequency of all the tokens combined. So after getting the probability score, what might happen is for some representation, we can encounter same probability value. So in that case, we pick the probability values which is encountered first by the model. So after getting the probability scores, we choose our starting representation based on best probability scores. So after this point, we calculate the loss function. So loss function is basically the multiplication of frequency with their negative log probability values. So for example, for jug, it is 10 multiplied by negative log of probability of jug. So after this, we iteratively remove the tokens and recalculate the loss values. So for example, if we remove JU, then in that case, we'll have to represent jug as JU and G, and we'll have to use the updated probability score of 0.001 instead of 0.005. So after doing this, we saw that the loss function decreased from 89.44 to a lower value, which means there is an improvement and we can remove JU. So this process is carried out iteratively till we reach the best loss function value. So now let us come to WordPiece. So WordPiece is used by BERT and it can be seen as the combination of BPE and Unigram. So as we have seen in Unigram, it starts with all the possible combination. Instead of that, first we implement BPE to get an optimized vocabulary. But as we know, it could also be an ambiguous vocabulary. So on top of that, we implement Unigram to remove the ambiguity and finally get an optimized and non-ambiguous final vocabulary set. In this video, we'll talk about BERT architecture. So let's get started. BERT basically stands for bidirectional encoder representation from transformers. It is a transformer-based machine learning technique for natural language processing. It can be seen as an encoder stack of transformer architecture with a variable number of encoder layers. So we have two variants, BERT base and BERT large. BERT base uses a 12 encoder layer, while the BERT large uses 24 such layers. It also have bidirectional capability, which basically means that the model can take words from both the sides. So this allows the model to read all the words in a sentence at once, which is not the case with the directional model, which can only process the data sequentially, either left to right or right to left. Now let us look at transformers. So transformer basically includes two important blocks, encoder and decoder, where the job of encoder is to map the input sequence to a sequence of continuous representation, which are then fed into the decoder. Because BERT does not use decoder, let us only focus on encoder and see what are the different layers that are used. So encoder uses self-attention and feed-forward layer, where the self-attention layer tries to see the relevancy of each word with respect to the other words in a sentence, and the output is representation of attention vectors. These attention vectors are then fed to the feed-forward layer. The purpose of the feed-forward layer is to transform the attention vectors in a format that is acceptable by the encoder layers. Now let us look at self-attention and try to understand how it works. So self-attention basically tries to get the word representation in a contextually aware manner. So let us see how it is done using this flow. So let's suppose we have two sentences, bank of river and bank give loan. In the first step, we do subword tokenization. We have covered this technique in our previous video, so please refer to those videos for better understanding. After passing the sentences through this layer, we get individual words, that is bank, of, and river for the first sentence. After this step, we pass it through the embedding layer, where embeddings are generated. Embeddings are basically numerical representation of these words. So for example, V1 represents the vector representation for the bird bank, and V2 for of, and V3 for the river. After this, these embeddings are passed to the attention layer, where each vector interacts with the other to generate the context. For example, V1 interacts with V3 to learn that the bank is being talked about in the context of a river. So this is being reflected in the attention layer output. So here Y1 is the updated vector for bank, but it is contextually aware that it is a river bank. Similarly, if we would have used the other sentence, that is bank gives loans, till here the representation for the word bank would have been the same, but after passing through the attention layer, it would have learned that we are talking about a financial bank. So this is how self-attention works on an overall level. Now let us look at pre-trained models of BERT. So BERT works in two steps. It was trained with large amount of unlabeled data to learn the language representation, which is called the pre-training. It was done with the help of Wikipedia data, and two different techniques were used: masked language modeling and next sentence prediction. In masked language modeling, 15% of the tokens were masked, and BERT was trained to predict them from the context. So basically, we mask the birds, and with the help of other words, we try to predict what would be the suitable word for the masked position. And the second one is next sentence prediction. So here, for a sequence of sentences, we try to see if those sentences are related. So this we have covered these concepts in our previous video. Refer to those videos for better understanding. The second part is fine tuning. So here the pre-trained model is used from the trained checkpoint, and we use it on a small amount of data for our purpose, and retrain it from those from that previous checkpoint that is done in the pre-training part, and use it according to our targeted task. So yeah, this was all about the BERT. Thank you. Have a good day.